All right. So, yeah. So what I wanted to show you guys. So, just also to recap briefly what we discussed today was that for the project part, we are going to follow different modules, and as I mentioned before, there is an incremental work that will happen throughout the modules. And at the very end of the semester, we will have a defense where you will present basically the integrated solution, which includes module 1, 2, 3, 4, 5. And today, module 1 is mostly about for you to get familiarized with the tool, and then also to familiarize with the creation of orbits like the one that we did this morning for the SAT part. So always, as I said before, the central place for material is the Moodle site that I'm showing here on the screen. In this site, there is this PRJSAT part where there is this project document that when you click here, you will get to this document that is shared among all the modules. So this is a document that we always try to polish a little bit, and thanks to some of your comments already, I noted a few improvement points. So if you have any suggestion on how to make this document clearer, just let me know. I will improve it. But more or less here in this document, we have like a very short list of the 5 modules that we will go through in doing the semester. Today we're focused on module 1, where, as I mentioned before, we introduce the basic of STK. And basically, we want to create a simple satellite constellation based on what we learned today. And basically, we are trying to see how this constellation can visualize each of the satellites, if there is any opportunity of connecting each other, and so on. This is what we're going to learn today. But of course, first, we're going to start with the installation of STK. So here, I think one good question that was asked this morning, the basic things are here in the first link, the pro version. Then if you really want to explore more extensions and so on, you can download the other part, but it's optional for the moment, unless in your specific application you need something interplanetary or something that is a bit weirder, then you can just go ahead with the base version. Then just follow the instruction for installing STK. I think there are a few folders there. It's just a folder that says STK version 12.5, period, nothing else. That is the version that you should install. Again, this is, as I mentioned before, it's only on Windows. Once you have STK installed, you can also, there's another window that appears at the beginning that lets you choose between space and enterprise and so on. Just the space one is good for what we're going to do on the project. And yes, to execute STK, as I mentioned before, STK is a licensed tool. So to run the tool, you will need to reach a licensed server that is deployed in INSA network. But also some of the ports are not public available on the INSA network, so we need to create a tunnel. So the very first step is, before executing STK, is make sure that you are connected to the INSA VPN, right? So this is the first step. And once that you are connected to the INSA VPN, so of course, like you just use the client, you might have to make sure that you are connected to the VPN. And once you're connected to the VPN, we need to create this tunnel so that the STK tool can reach the port that the license server is running and listening on. And to do this, you can basically have 2 options. If you're using just Windows 11, then just copy and pasting this command over here with the exact URL that we have here. You don't need to change this with your username. This is just one of our colleagues that is hosting the server for us. Just copy and paste this and run it. So I will just do this on my side. I'm moving here to my Windows machine. So just basically, you just need to open like a standard console. This can be a power console or a standard one. And then just basically pasting this. Let me just copy again, just to make sure. Copy, just make sure that I'm pasting this in a good way. Right, yeah. So I'm just pasting the plain text. So basically, in this, I'm sorry, maybe the font is not super big, but essentially what we're saying here, SSH, well, we are basically tunneling port 1055, 1056, and 2325. from the license server to our local machine, right? So I'm just going to hit enter here. Oh, sorry, this one. And then it will ask for me for the password. And the password is just the same that we have in the document. For you to look at here, should be tunnel user. Let me see where the password was. Okay, yes, tunnel user, right? Here, tunnel user. And then once the password is okay, as I show in the screenshot on the shared document, the cursor will stay there. And this means that the SSH is connected and that the tunnel is open. Then when you run STK for the first time, you will likely go to this, it will ask you for configuring the license part. And let me show, you should get access to a Windows like this one here. And I think this is also explained here in the document. So you need to configure the local port 1055 to connect to localhost. This is a little bit boring, but once you have this done, it's one time and that's it. And this is what we are seeing here. So we have, just ignore the first one. This is another server I'm using. But just put the port 255, the local host. And eventually, if you then run this test button here, it should show something green, I guess. Right. So if you run the test here, it should have green, a green tick. That means that the local license server is connected, the local license client is connected to the licensing server. And after you do this, STK should be good to run, basically. Are you guys in this step already? Are you, anyone needs any help? Where are you guys standing? Are you downloading still? Okay. Right. I guess if you are into the Wi-Fi thingy, maybe you. And really don't install the VPN. Yeah. Really? Okay. I'm using the VPN since many years ago, and it's okay on my side. But yeah. Stopped working. Okay. Okay. Benoit, on your side, all good? You guys have installed. Are you installing it as well, or? Okay, you're. Okay, good. And you guys, the three of you are okay? Okay, great, excellent. Perfect. So then let me go away from here. Stop sharing here and let me start sharing this one. And so now, before going into the details of Module 1, I can make a quick tour over the tool so that you, while I record the screen so that we all are on the same page here. Right. So let me zoom full screen. So are we? Can we all sit here on the same screen? Okay. So as I showed this morning, the typical first step is to create a scenario, right? An STK. If you want to try to follow me, so you do the same on your side. Of course, there is a name, as I mentioned before. You can enter a description, like with general things, where you want to save it. And here you set the start and end time of the analysis. This is, I mean, I really went through quickly this morning over here, but this is important when, depending on what type of mission you want to analyze. How many days do you want to analyze on the tool, right? Because if you see today when I run some animations, if I let it run enough time, then the orbits from one moment they disappeared. Because what you're basically telling STK with these two dates here is when to start computing and when to end the computation. And this is only the period where the orbits of the satellite will be propagated. Outside these periods, you will have no data to show, right? So this is important. Something interesting, for instance, you can do is sometimes it's practical. You can say here plus 4 days, for instance. If you do this, you can have this, and then we just from the first date here, the 4 days, it will just propagate it over 4 days. And then you click OK, and then it will set up the things for you. And then we basically, the SDK loads the main user interface window. Sometimes it's a bit slow. Right, and then I'm just going to close the create part here. And yes, as a recap of what we saw this morning. So this is what we typically see in STK. So we have a top bar with a different menu on the top. We have this column over here, which is the object browser. Everything we create on the scenario will appear here as an object, and this is a tree and a hierarchical tree. And then you can see that, for instance, you can create a satellite, and inside a satellite, you can create an antenna or a sensor or something. And this is like a hierarchical object browser model. Here you have 3D and 2D windows that you can add, remove, or use as you need. You can have multiple 3D windows, multiple 2D windows. So you can have, typically, if you have like a large screen or something, you can have one window focusing on one satellite, another window focusing on a ground station, and you can have like everything simultaneous to visualize your scenario. And underneath, there is a timeline. So here underneath is where you can scroll the time back and forth. So you can click here on the pointer and moving one direction or the other. And this is by default at the beginning, the duration of the full scenario until the end. When you run a very large scenario, something that is useful is to, and you want to be very subtle on the time dimension that you want to change, you can here on this upper timeline, you can basically narrow down the time window of the analysis that you're using. Right, and therefore the scrolling that you use is kind of a finer grain, and you can navigate over time more specifically there. Then, as I said before, you can here in window, you can basically view. You can have new 2D graphics, new 3D graphics, and you can have multiple windows at the same time. So what I was doing this morning, you maybe have seen, this is kind of a very important button, the one on the top here. This is where basically you say insert objects. This insert objects, I opened this menu that I also used this morning. I just want to replicate the creation of a satellite, and then we're going to explore some of the other options. So when you click satellites here, you have on the right-hand side a bunch of options. This morning, we only use Orbit Wizard. Let's do it again so that we can have it also here on the video. And by default, the type of orbit in the Orbit Wizard is a circular orbit, so it's super easy. As I said before, you can define the inclination here in degrees. You can define the altitude of your satellite and the right ascension of the ascending node, which is, remember, the position of the orbit along the equatorial plane. So you can do this. Once you're happy, just click OK. And we have our first satellite created. We can animate in time back and forth with your timeline below, or you can just use a display and pause and stop button. You can control the speed up with these arrows to the up and down arrows. You can control here the speed up, and with the red button you reset to time 0 of your period, and you can very easily navigate in time and animate the scenario as you need. And for instance, something that I can quickly show now. Let me show this vertically. Sorry. Something you can do, for instance, let's say that, of course, you can navigate on your 3D window as you need. With the wheel, you zoom in and zoom out. But sometimes it's useful, you want to focus, for instance, on satellite 1, and you visualize satellite 1. You can right-click on satellite 1 here, and there is this zoom to button on the menu. When you do this, your 3D window basically is completely focused on the satellite you created. You can zoom out with the wheel or with the secondary button, and you can zoom out as much as you need, and you see that the camera is now completely focused on the satellite you created. Let me just open this border. And even when you animate this, basically the camera will follow your satellite. And this is where having different 3D windows can play in your favor, because you have one camera focused on a ground station, another one on a satellite, and so on. Then you can go back to the default view if you use this button up here, which is home view. You can just click there and then you reset the view to the default one. So if you right click the satellite, there is also the first button here, which is properties. When you click properties, you open this, let's say, quite packed window, but here on this left menu over here, you can choose the category that you want to analyze. We typically just basic and orbit for the moment is what we're looking at. And this basically opens this window that we have on the right-hand side. And what can we see on the properties of the satellite here? Take a look. The first element here is propagator. This is what we discussed this morning. This is the mathematical mechanism or the algorithm that the program will use to compute the path of the satellite. By default, it has a J4 perturbation. J4 is a propagation algorithm that considers up to the fourth polynomial element of the Earth-Oblatness model, basically. In any case that you need help, I mean, the help of STK is typically quite good online. So you can click help and you immediately go to some web page that explains what this is, if in case you forgot. So for instance, you can really see here that J4 considers the most important Oblatness effect. So this is basically what we discussed today during the lecture. Then you have the central body, but default is Earth, right? Because everything that you configure here, all the orbital parameters are for satellites that are around the Earth. But if you're interested in something interplanetary, then you can also configure another central element like Moon and Mars, and you can add satellites also in another planets. Then the most relevant part of this window is actually, so let me see if I can actually draw something. These 6 elements here. And these are precisely the 6 Keplerian elements that we discussed this morning. As I mentioned, some Keplerian elements are interchangeable and you can use one or the other. So for instance, let me get rid of this. So for instance, semi-major axis can be exchanged by many other ways of expressing the same orbital shape parameter. Eccentricity can also be defined by others, right? And you can change equivalent parameters, equivalent way of expressing the same parameter. So for instance, typically you can, sometimes it's practical, especially with circular orbits, to instead of saying which is the semi-major axis, which is from the center of the Earth to the altitude of the satellite, you can I just want to express altitude, for instance, right? And since if you see what happened here in this, since I am in a circular orbit, I just have apogee and perigee altitude, which are the same. So I have 500 kilometers for both. And if you remember, this was the parameter that we chose when we created the satellite in the first time, right? Then we have a 90-degree inclination. The argument of perigee, someone remember what this was? Exactly, right. Within the orbital plane, right? So the argument of perigee actually tells us how is the orbit rotated inside the orbital plane. In this case, we are in a circular orbit, so this really doesn't make any change. Then we have the run angle, which is the position of the along the equator. And then we have the true anomaly, which defines what? Do you remember what was the true anomaly? The position of the satellite. Perfect. And maybe this is a good opportunity to discuss something interesting, because let me switch here. I will go back to the beginning of the simulation. So if I change the true anomaly to 90 degrees, let me see if I can fit the 2 windows together so we can change this in a more convenient way. Tac. Okay, right. So if I change, so I had 0 true anomaly at the beginning, right? So this is the satellite position. If my true anomaly is 90 degrees and I hit apply, my satellite moved 90 degrees, right? So remember, this is valid in a given time where these parameters are valid. So this is why changing from 0 to 90 defines the position of the satellite here in the orbit, right? At the given time. Something that is interesting is that I mentioned to you that, let's go back to the 0 state, that the argument of perigee has no impact on the orbit because it's a circular orbit. But this is not totally true, Because if I do 90-degree perigee and I hit applied, what happens? The satellite moved. Why is this the case? Because the satellite is still a true anomaly 0, but it was the full plane of the orbital plane that rotated 90 degrees. So in the case of a circular orbit, changing these two parameters has the same consequence, right? In the case of a circular orbit. If it is elliptical, this is not the case. But just for you to understand what's the impact of the argument of perigee, there is some impact in satellite position as well. And something I wanted to tell you is that also one of the main parameters in this part over here is also the time, right? So this is why maybe I want to make focus here. So these are, as I mentioned today, the 6 orbital elements are valid in a specific time frame. And this time frame is defined by the orbit epoch. So all these parameters that I show here are for September 24, 2024 at 10 a.m. UTC time. So if you change the time, your satellite will still be on the same position that we're looking at now, but the time will be different, right? So that's important also, that time is a major element in the configuration here, right? So this is where the orbit epoch, by default, the orbit epoch is set to the beginning of the scenario, or this is by default. You can change it by hand if you want, but typically you don't really need for that. Another important parameter here on this window is the time step size. This is on the visual side, it has almost no impact because, I mean, whether if you compute the position every 60 seconds or every 10 seconds doesn't really make a big difference because the animation seems rather smooth in general. But when we start exporting data, which is what I want to show you next, then this is important because of two things. Because this gives you the resolution of the data that you will export. And this will guide also the computational effort that STK is doing under the hood to compute such a data. And this is important in larger scenarios. When you have scenarios with multiple satellites and you want to export the scenarios of 1 week, 2 weeks, or 1 month, then if you hit compute, then STK might be computing for many, many minutes. So sometimes when you want to export data and computation is getting quite heavy, sometimes remembering which is the time step that you're using is important. There is something else about the coordinate system. I don't get into this too much because it's super boring and difficult. By default, I typically leave the same one. Everything is, of course, important, which is the reference system that you use. And typically in space, we have two families of coordinate systems. We have inertial coordinate system and non-inertial ones. Inertial coordinate systems are XYZ axis that rotates together with the Earth. This means that when you export data out on XYZ, you will be plotting everything related to the surface of the planet, right? And this is convenient when you have ground stations. Let me add one ground station also to realize what I'm trying to do. So I'm only inserting an object here, and here I'm going to choose facility, right? A facility is typically a ground station. So what I can do here is just going to insert default. I don't want to define too much. I hit close. And here we see in the object browser, we have a new facility. And by default, this is, of course, United States. And this is our ground station. And I can also zoom to here. And we have our facility there somewhere in the US. And we have our satellite that passed by over that facility eventually. So when and going back to the coordinate system, when you want to export the XYZ position of your facility, which you can do, of course, as I will show you in a few minutes, and you're using inertial system, the XYZ position of facility is just one because it rotates with the Earth. It's fixed with respect to the Earth. But if you're not using inertial system, which is an XYZ that is fixed with respect to the celestial sphere, not with respect to the Earth, then the facility XYZ will be also variant in time, right? So choosing the right coordinate system is important depending on the analysis that you want to do afterwards. But as I said, I mean, I don't really get into this detail, but if you just be aware, if you ever export data and you start to, you need to consider this, choosing the right reference system can really facilitate the analysis quite a lot. Questions so far? Are you able to more or less follow up what I'm doing? Great. Of course, very stupid thing. You can rename, right? Things as you please. So you can say ground station, rename. Let's put Leo 1, and this is more or less what you have, and you can animate and you can visualize, etc. What you have seen. Let me move more into the analysis part, because so far everything is, the visual part is nice to generate intuition, but now eventually we want to get some real numerical data, right? To analyze and to make a plot or make a script to parse the data and make some analysis. Sure. In STK, this is done by means of this button up here, which is the report and graph manager. So if I click this, another window is open. Let's see if I can zoom this out here. The resolution is not helping a lot. Something I can do, I can try to make this float. Yeah, maybe I will try to manage this. Maybe I can close the timeline view. Okay. That can work. And what do we have here? So here is basically, I can filter out by type of objects on the scenario. So we have one facility and we have one satellite. And here on the right-hand side, we have a bunch of report alternatives. So I have one, you should have this my style, should be quite empty on your side because these are things that I created on my side. But if you open this install styles, these are default reporting alternatives that you find on the tool for a LEO satellite, for LEO 1. Let's try to explore what they have and try to choose one for to visualize. So one of them, let's try to see these classical orbital elements. You can double click and this will open this type of reporting views, which are text-based most of the time. And this is the typical data format that you have in STK. You have like a time column that every 1 second, in this case, actually provides a value. This is something that you can change also up here. Sorry, every 1 minute. So you have here 60 seconds. You can configure this to 30 seconds, and it will change the resolution of the step here. It's very similar to the time step that we saw on the other window. And what I'm basically plotting here in this report is every single Keplerian parameter that we studied this morning for every time step here. What happened? Remember that the orbital epoch that we configured was September 24 at 10 a.m. So in this moment, these orbital parameters are valid. 0 eccentricity, 90-degree inclinations, run angle, argument of perigee, true anomaly, close to 0. I mean, it was actually quite close to 0. Let me see if I can go back to this window on my satellite. Just clicking here, properties again. So you see true anomaly in my satellite was 0. And what I'm seeing here is that at that time is pretty much 0 degrees. So this makes sense. Actually, the mean anomaly as well. And what do we see here? That when we start sampling the same orbital parameter 1 minute afterwards, the true anomaly is no longer 0, but it's 3. So what is this actually telling us? If I go to the satellite window here and said, well, now I want my orbital epoch to be not 10:00:00, but 10:01, which is 10:01 minutes, and then here I go to true anomaly and put 3 degrees, I'm talking about the exact same orbits. What's happening? True anomaly in time, it moves forward because the satellite rotates. So the satellite position moves around the trajectory, around the path. And therefore, true anomaly is one of the parameters that evolve in time. Okay? But the other parameters, they don't. Eccentricity stays 0, right? Inclination is still fixed to 90 degrees. Run is also fixed. And I mean, you can basically go down to the end and it's pretty much fixed. The only thing that changes is a true anomaly or mean anomaly that defines the position there. Yes?
When you enter the dates, the time on like PC, I mean, is it like the real world, the sense of this, when you enter the dates of the impacts?
I mean, when you change the date, you mean here in the orbital, in the satellite parameter? I mean, just we can try that. Let's see what happens. The only impact you will see is that the orbit will change. Let's try to visualize it here. Let's try to put that we are moving. It is connected to the real world. The planet position and the sunlight exposure, it is, definitely, yes. So I only changed 10 minutes here of the orbit epoch, and you can see the satellite position changed, right? So, I mean, if you change the time epoch, these things changes. And maybe we can do these experiments also. I did put 10 minutes. Now I can go to the report again. The report still shows the old data. This is relevant. I changed the satellite parameters. The report has the old data. There is a refresh button here that you need to click in order to recompute the parameters of the report. And now you see that since I moved 10 minutes forward in the other epoch, I then get true anomaly 0 at the same time that we had before, right? At 10:10 now, because I moved 10 minutes forward the window of the orbital parameter. So I'm starting before 0 and I get to 0 10 minutes afterwards. Make sense so far what I'm showing? Good. Another comment I can make now is this one. So yes, please.
All the parameters not changing because we don't have enough time for it, because we saw that because of the perturbations. All the parameters of perturbations.
I was going to that point. So we have chosen the propagator to be J4. J4, if I open the help that I open here, so let's make a quick read. Two-body, J2, J4 are analytical propagators. Analytical propagators are important because this means that the position of the satellite is computed by means of a mathematical equation. And this is in contrast with numerical propagators, because numerical propagators, they need to simulate really the accumulated effects over time. Analytical propagator is just one input to an equation, the equation outputs, one mathematical calculation, and I know the satellite position, super fast. But analytical propagators typically do not account for three-body problems or n-body problems, because n-body problems need to accumulate the effects over time. For those type of effect, we typically use numerical propagators. Two-body, J2, and J4, these are analytical, that generate ephemeris by evaluating a formula, what I'm basically saying. Ephemeris is the word to refer to X, Y, Z position of an object in time. Two bodies formula is exact. The formula generates known solution for a vehicle moving around the center, blah, 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 but it's not accurate model of a vehicle actual force environment. This is what I said this morning. I mean, two bodies really quick. You can understand the general condition, but it's not super accurate. J2 perturbations include the point mass effect as well as the non-dominant effect of the asymmetry in the gravitational field, the J2 term in the gravity field, representing the north and south hemisphere of flatness. So J2 only considered a sphere that is like only stretched and pushed on the vertical dimension. J4 additionally considered the next most important effects, which are the J2 squared elements of the polynomial, which means that this only considers some other variations on the gravitational field of the planet. But none of these propagator, and this is the important part, model atmospheric drag, solar radiation pressure, or third body gravity. Because of this, basically, we are just seeing quite a simplistic propagation model that renders this parameter quite stable in this direction. But even J4 could have an impact in this. So let me just try to put this in a thicker step to see if I can get to visualize the effect. Maybe 4 days is just not enough. Let me try to do something to see if I can get to show what I wanted to show to you. I can go to a scenario properties and change this to be, let's say 90 days. So I can simulate like 3 months. Hit apply, I hit OK, and I refresh this out. No, I need to refresh also the satellite. Let me just check here, just J4 apply. Let me see if this works. No, wait 1 second. Where was my timeline? Yeah, sometimes this timeline view. Let me see if I can. I just want to check. Right, the orbital properties are there. Okay. Now I want my report to generate the data for the full period. Check this out. This is something that typically happens on STK. I put 90 days, so this is 3 months of propagation. And 3 months is a lot considering that one LEO orbits every 1 hour and a half. So this will be quite an intense simulation, and STK basically warns you that you're using, this might take some time. Let's try to hit yes and see if my computer can handle this. Yes. Now I'm going to show state value. It's a bit slow. And let's try to put the day here. So here we have 1 day. And basically the orbital parameters remains pretty much stable, even though we are using a J4. How can I scroll to the right-hand side here? Yeah, let me just, I think I will make a point here. So run angle is not so stable. You can see it moved from 138, 0.6, 0.7, 0.8. So if you understand what's happening here, this orbit is, even though it's ideal orbit, its run angle is shifting slowly on a day-by-day basis. I mean, it's not super fast. You see that 0.1 every 2 or 3 days. And it seems little defects, but if you just propagate over the 90 days, in 3 months, you shifted 1 degree at least or more. And 1 degree or more, if you plot this, project this to the surface, these are thousands of kilometers. It's 1 degree of longitude on the planet. So it is a significant variation. And this is because we are using the the J4 propagator. Let me try to make also a quick experiment here and set my LEO 1 to use just the 2-body propagator. I hit apply. Let me see if I need to refresh this out. Right. If you see, I just have selected the 2-body propagator, and now the run angle is starting. Because what's happening here? If you just consider the point mass, then the orbit will not shift. It's just an ideal orbit. But when you consider the gravity variation of the surface of the planet, then this number will shift. And I've been quite, and this is a humble shift because I am using quite a polar orbit. Let me just go back here to my satellite. I will go back to J4. I will click apply. And I will try to see what happens with a 40-degree inclination orbit. I will apply, and let's see if I can refresh. Now you can see that the variation in run angle is far more drastic. What happened here? At the beginning, I had a 90-degree inclination orbit that was pretty much a polar orbit, right? And now I have an orbit which is 45 degrees inclined. The nice things of polar orbits is that the first coefficient of flatness pretty much cancels out, because you basically go over the pole, you feel more force, then you feel less force, and more than print, and you basically compensate throughout the trajectory. But when you start to be inclined, then this doesn't compensate anymore, because you're being pulled down when you are on the upside, you are being pulled down, and when you are on the other side, you're pulled on the upside. So your orbits start to rotate in this direction. It's tried to get closer to the equatorial plane. Maybe if I animate this quick enough, I might be able to show you how this looks like. If you see, the camera in STK is frozen in the celestial sphere. My camera is fixed. And if I just animate over the 90 days, you will see that the orbit precesses. This is actually a precession movement. And this is the variation of the run angle just because of the gravitational inaccuracies of the planet. Let me just for the sake of clarity with you guys, let me get here, just 2-body again, just to show the difference. Okay, hit apply, go back. And with 2 bodies, this is what happened during the 90 days. There is no precession whatsoever of the orbit. right? So I'm moving here to J4 again, apply. And again, we see the precession effect. Make sense? Questions or comments so far? Good.
The lower the inclination and closest to the equator, and the stronger the position, like the
Yes,
fastest.
exactly. I will fall back to the slides I used this morning to make a point here also about perturbations. Okay, let me go quickly down to one of these plots. Width speed, run shift. This is just to take a look at this plot. What we're seeing here, sorry, the projector again is not super cool. So this is the run shift, namely the degrees per day of run shift that we have for different inclinations because of the Earth obliqueness. There is something interesting there is a really interesting thing to actually show here. So as I get to 90-degree inclination, then you can see what I mentioned before. The run shift is close to zero because you compensate most of the effects. But when you start to have more inclined orbit, up to 180 or zero, which is basically the orbit which is completely compressed on the equatorial plane, then your daily run shift start to become more important, especially on lower altitude orbits. The lower the altitude, the more important the effects, which is of course because you really feel the non-homogeneous gravitational field of the planets. So you get the most value here. What I'm plotting here in this red dashed line here is something quite interesting, which is this run shift that particularly is minus 0.9863 degree per day, which is the exact shift that you need, so that in 360 days, namely a year, you make a full turn of the orbit. What do you think? Why do you think this would be important?
To give more distance to things that are all of the Earth orbit.
So, any other hypotheses? So let me reason one more second what's happening here. So so for instance, if I am on 70-degree inclination and I am on an orbit which is 2K kilometers, then in this point, my run angle will precess at one full circle in 1 year. So my orbit will do 360 degrees in 1 year. Exactly. An orbit that fits, that is at the crossing point of this line here, is an orbit that has always the same profile with respect to the sun. If the orbit is if the sun is there and this is the orbital plane, my orbital plane will be always rotating together with the sun. Likewise, if the sun is there and this is the orbital plane, the sun will be always looking to me in that direction, right? Because I will rotate together with the sun as the Earth goes around the sun. The orbit always has the same attitude or the same orientation with respect to the sun. And why would this be something interesting?
The energy to charge the sunlight.
Exactly. This is one of the main reasons, because this means if I always have my orbital plane with respect to the sun, I can even put my solar panels on one side of the satellite, because I can just have that side of the satellite looking at the sun all the time, right? And my orbit will precess together in a way that sunlight will arrive all the time. That is one of the reasons. The other reason is that since I am rotating together with the sun, I always have the same luminosity condition under the satellites. If I am basically on the afternoon or night. I can actually show this out in STK to explain. Let me try to let me try to. I need to exit. Okay. Let me get rid of these two elements here. These orbits that precesses together with the sun are known as heliosynchronous orbit because they are synchronized with the sun. And in order to avoid and facilitate things, one of the type of orbits that we can choose in the orbit wizard is sun-synchronous orbits. So if I choose sun-synchronous orbit, STK will do all this computation instead of me doing the hand mathematical inclination slash STK help me, of course, to do this. And the only thing I can configure, I can just configure the altitude of my satellite here. So I guess I want a satellite of 600 kilometers. And then I compute the local time of the ascending node or the descending node, right? And you can basically, this is the run angle in essence. Let me put a wide orbit here. And STK will create me an orbit which has an inclination and altitude pair that fit the intersection of the curves I showed you before, right? So if you see here, if I change the altitude, I'm not able to touch the inclination, or if I touch the inclination, I'm not able to touch the altitude, right? So let's say I want, as I said, it's like 600 kilometer satellite. I will click OK. And this satellite that I have created here is a sun-synchronous orbit. It's a satellite that is synchronized with the sun. Let me sun-synchronous orbit 1. I will name the satellite. I will go here into properties. Let me just, for the fun of it, just make it. I will try to imitate a realistic configuration for observation satellite, which is satellites which are known as afternoon or with orbit in the afternoon. I will explain why. Just give me 1 second. I will try to. And what I'm basically doing here is something that you will need to do in the practice, just to iterate on orbital parameters to find what you need. So 200, 100. There you go. It's actually I iterate. I hit it. So if you see what I did, I basically have a satellite which orbit is basically, if I am the sun, right? I am illuminated the satellite. Yeah. And if my orbit is really sun-synchronous, my satellite will have permanent sunlight condition. Because I am the sun light gets in this direction. And hopefully, if the orbit is sun-synchronous, it will accompany the sun all the time, and we have a sunlight hitting all the time. Which, of course, I mean, for a vision designer, this is wonderful, right? Because you don't have eclipse. The satellite is never on the shadow. You get constant energy flowing into your satellite.
Does it mean that similar to the geostationary orbits, people want this?
Exactly. Engineers, like the people that is in charge of the power subsystem of the satellite, are super happy because they have sunlight all the time, right? So they don't need to. In principle, a satellite operating in such an orbit might operate without a battery even, because you have continuous sunlight. In practice, this doesn't happen, but really the requirements of a battery is neglected here. Yes.
Could this be useful for those like if I have an constellation using the like that?
Yes.
So,
Right, because in the Lagrangian point also you are. I mean, as long as you start to go away from Earth, you typically have permanent sunlight exposure. I mean, you never get shadowed by almost anything.
Like communication between a satellite that's maybe not on Earth to another one.
Yes. You can compute an orbit such that it precesses at the rate that you want, so that you can continuously reach out to someone at a given point. Yes, but this maybe need to be computed by hand, but in principle, you should be able to compute that. Yes. So now let me see if I can make this work as I expected. So let me just check first. The SSO satellite has J2 perturbation. Let's just be sure that I use the J4. 1, 2, 3 window. And let's see if I can animate this. You can see I'm animating this, and the satellite is rotating together with the shadows last light condition of the planets. What's happening here? Of course, this is not ideal because, as you know, the Earth is inclined with respect to the solar plane. So sunlight actually goes down and up, winter and summer, essentially, for the planet, but the orbit is still on the same inclination that before. So more or less, the plane rotates with the sun. So the sun is always looking at the same direction from the plane, but there is this up and down situation where eventually you might get some eclipse at this point in the upper part of the orbit. It's still not much. So you see the sun over there, right? So at this point, I think we are right there. There's an eclipse condition, right? In this point. Even though the orbit is precessing together with the sun and it's looking perfectly into the sun direction, the fact that the Earth is inclined with respect to the sun plane will still generate some eclipse. This is why I say that actually you always need some batteries and satellite in the end. But it's an exceptional condition and not a permanent condition. And these are known as sun-synchronous orbits. Now let's see what happens if I can just again to reinforce what we were discussing. I go to two-body problem, to the two-body propagator, and I go here. And you can see that this is not happening anymore. As I get close to the end, I have the orbit completely, right? The orbit is not precessing. Again, the orbit is fixed, which is not true. I mean, this is not the real one. This is the ideal computation. And this is why you can, some of the like astrodynamics engineers, they really profit from the perturbations to have the orbit make things that are useful for the mission, right? Even though these are perturbations, which has like a negative connotation by the word, but in fact, it can help you to have effects that are useful for the mission in some way. Questions so far? Comments? Yes, let me go back to the reporting part so that you can. You know what I can do? I thought something interesting to share today also. I will, first of all, I will reduce the scenario duration so my laptop doesn't burn to death. You can see my coolers running full throttle here, right? This is because even though it is J4 is super efficient, the computation of 90 days is you need to compute is quite intensive. Let me just get rid of this one and go back to our LEO and our ground station originally that we have here. So something interesting that we want to do as communications, let's say communication people, is we want to understand when this satellite can actually communicate with the ground station that we created, right? So we know if we animate here the time, we see that, for instance, here, if I animate now, this satellite, we see that passes very close to the ground station. So ideally, in this moment, this satellite should be able to talk to the ground station. If I zoom to the ground station here. By the way, if you leave it some seconds, the STK to load the data, it loads the beam mapping information, and you should copy the altitude and the details of the location of the ground station. So here, I think the ground station by default is placed in the offices of the company that create STK in the US. But if you start zooming out, then we should be able to see, right? So this is, this is definitely a condition where the passing by satellite should be able to talk to the ground station, right? But of course, we want to compute this like automatically in a more accurate way. And the way of doing this in STK is by means of a tool that is called access. So computing access from one object to the other. And this access tool is this button over here. If you leave the mouse over, you will see that one over there with the green and the yellow thing. So you can open access here. And here you see access for, I want to select the source object or the ground station. And here I can select the target object I want to compute access to. And I can just click compute here. Once it is computed, it is computed, right? So let me just again close my timeline here. And I can just click access on report access. Maybe I don't have any access. Maybe I need to reset this a bit because I changed the duration a lot. Let me see. Oh, yes, I do have accesses. I don't know what happens. Okay. So once this is computed, one of the things that we visualize now, if you see now, we have a link between the ground station and the passing by satellite. So, and this basically, this line appears as soon as the satellite has line of sight condition with the ground station. There is a visibility condition there, and then the satellite hides in the horizon, and there's no more link available. What we can do here is to go to the report part, and here we have actually the I can zoom out with the numbers. Yes, so we have actually the different episodes contacts between the two elements. So we can see here that 24th September at 15:17 seconds, 172 milliseconds. There is a contact that is starting between these two elements. So between Leo 1 and ground station. And this contact starts at azimuth position of 170, an elevation of 0, and a range, which is the distance between the ground station and the satellite, of 2,500 kilometers. For those azimuth and elevation are the two key angles for orientation. Azimuth is measured from the North Pole, and this is azimuth 0, azimuth 90, azimuth 180. Is the rotation in this plane, and the elevation is the elevation from the 0 in the horizon towards the sky. So of course, since I'm only considering line of sight, the first millisecond I have access to the other element is at elevation 0. From the ground station perspective, is 0 elevation, because the satellite is black, right appearing in the horizon. And then as the satellite passes by over me, it goes to 2, 3, 4, 5 degrees, 4 degrees, 3 degrees, 0 degree, it goes back again to 0. Right? Is this do you think this is a good pass or a bad satellite pass over the ground station?
A bad pass.
Why?
It means like it's not really aligned, so it's not like going this, but more like over there.
Exactly. That's right. If this were a good pass, I would try to get to a number which is close to 90 here, because it would be an elevation that starts in 0. I would have the satellite right on top of my head with 90, and then it should go back again in the horizon on the other side. But here we can see that it goes to 5 degrees. And let me actually show something that helps a lot. Let's say that I want to investigate visually what's happening here. I can just right click here on the time and say time, set animation time. And this will move my timeline to exactly this point. And now I can go to my windows. If I can get rid of this zoom thingy. And this is the exact moment that I have selected on the report part. And in fact, it is as you mentioned, right? The satellite is essentially on the horizon, appears a little bit, and then hides back again. The maximum elevation, that makes sense. If you more or less visually, you can confirm that if this is 0 elevation, this is more or less 5 degrees. So it makes a little bit of sense here. And this was one of the passes that we are studying here. I can also go and animate to this time. And now this is the exact moment where the satellite will hide in the horizon immediately afterwards. And we can see here from the ground station that indeed, yeah, the satellite is pretty much in the horizon down there. If I just animate this a little bit more, the satellite is out. I am not able to reach it anymore.
Is elevation 0 to 10?
Yes, correct. And you will see that all other passes are actually have the same properties, right? So 0 elevation. This one is a little bit better and also longer. You can see that we get to 36 degree. And also we have much more timestamps. This means that it's a longer pass. We can also check this out. Right, so it seems it is a far better pass. You see that the satellite pass far closer to the ground station. The range is also gets to almost 800 kilometers when the satellite altitude is 500. So it's actually quite a good one. This one is even a better one. It's almost 90 degrees. You can see the satellite is passing by right on, pretty much on top of the ground station. So this is a good pass actually. And this is how you can basically you can just click here, save a CSV file, You can get this out as a CSV file. You can open this from your Excel processor or whatever. You want to parse this. Of course, I mean, what you typically do, what I typically do to work with this is I parse CSV5 with Python script, and then you process the Python script as you want, and you do the analysis that you want. So here, for instance, you can more or less automate this, get an export of 90 days, and then process this with Python and make a plot of the distribution of the duration of the passes, of how was the elevation, and so on and so on. So you can analyze a little bit there, how are these contacts and this communication opportunity between the satellites and the ground station. So for instance, Benoit, for the thing that, for when we generate a scenario for your studies, essentially this is what we are doing, right? So we are adding the satellites, we are adding the ground stations, we batch compute all the accesses, we process this in Python, and we can get the contact plans for ION or whatever out of it very easily. That this is basically the process. What I want to show you now is that in some cases, ground stations have things around. It doesn't mean that ground station, I cannot put my antenna to 0 degrees and start communicating with something at 0 degrees. I might have mountains, trees, something. So I might have constraints of elevation. So I say, I can have a link with a satellite, but only with an elevation higher than 5 degrees, for instance. And this is something we can also configure in STK. So I can quickly show you how to do this. So I can go here to my ground station properties. And of course, I mean, here in the properties of the ground station, I didn't mention this, but you can change the position of the ground station, the latitude and the longitude position of the ground station. Also the altitude, right? If you want to have a ground station that is on a mountain or it's a ground station that is on the valley, you can set the altitude. It will definitely play a role here. But what I want to move down here, if you have one of these menus on the right-hand side, is constraints. Here in basic constraint, you can constrain the moment where this ground station can really operate as an access element. One of these constraints is the elevation angle. And like I say, I want a minimum elevation angle of, as I mentioned before, let's say 10 degrees. So I say from 10 degrees to low, below the 10 degrees, this ground station cannot establish a link with a satellite. This is one way of putting this. You will see other constraints like ranges. So let's say that this ground station can communicate up to 2,000 kilometers and no more. You can also set this constraint here. So let's set this one to 10 degrees. I hit apply. I hit OK. I might need to recompute this access. Let me check. Maybe not. Yes, I mean, I didn't need to recompute the access. Here, I just refreshed the report. And now we see that the same path that we have seen before now starts at 10-degree elevation value, which is a little bit later now because you need the satellite to go up a little bit, and then the contact starts. So here you are basically narrowing down the angle of the ground station that the ground station can use to communicate. So if I zoom in here, then we see that this is the exact moment where the contact starts. And the satellite is already up in the horizon from some time already, right? So I can basically this is moving into, this is satellite, appears in 10, and should go out of range in the 10-degree elevation from the ground station. What I want to show you next. Let me go back to the default view. So one of the objectives of the module 1 part of the project is to create a constellation of satellites. The best way of doing this is to control this by hand, because in the mission that we work, that you will define in the next module, you will likely have multiple satellites, not only one. And the best way of creating constellation, if it is small, is to do this by hand. And for instance, one trivial way of creating a constellation is to, let's say this is a polar, let's put this as a polar orbit. And what I can do is basically I can just copy and paste these satellites and hit the properties of LEO2 and say, well, I want the LEO2 to have the exact same orbital parameters as the one, but maybe I just want this true anomaly to be 10 degrees farther ahead in time. So we click apply, okay. And you see, I have my 1 and 2 satellites here that basically flies kind of in a train formation, one behind the other. And this actually typically is quite a typical type of constellation shape. And I can basically iterate on this one multiple times. So let's say 20 degrees. Degrees. I think I went out too much. Yes, 20, 30. So I need a properties 30. Just to keep it uniform. Right. And then I have created like a fly constellation of 4 satellites that use the same orbital path, right? The same orbital plane. I'm just changing the true anomaly. So this can be a constellation or a mission of 4 satellites that flying behind each other. Just for you to, let's say, exercise your imagination. This can be a constellation where maybe this satellite has a infrared camera, this satellite has something more specific, or maybe this can detect a fire and this can take a picture of the fire. And this is where you can start to get some imagination there, how you can imagine a distributed mission with multiple satellites here. And of course, you can change the true anomaly, but also other parameters are possible. So I will just copy and paste DO1 here. It's going to call this DOB5, just going to change the color. And I'm going to create, instead of changing now the true anomaly, what can we change? Like the run angle maybe. Instead of 139, I'm going to do 110 degrees, so 49. $59. And 69. So I'm just changing the step of the run by 10 degrees. And now we have another constellation of satellites that also has a different property here. So basically, as you see, if I change the run, they fly all together, but they spread on the equator side because I'm changing this orbital parameter between each other. So this can be also another interesting constellation if we really want to get, let's say, maximum coverage over the equator area. But of course, this satellite will get very close on the poles region, right? So let's focus on this one. So if you see what's happening here, right? I mean, if with these exact orbital parameters, this will collide in the pole, right? But you have this effect. I mean, they get very close in the pole and they separate each other as they go to the equator area. So this is another, if you change that, the run angle, this is a constellation that you can get. And of course, you can combine, you can change the run angle and also the true anomaly, and you can get like a stair type of constellation, like one here, 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 and there, right? Combine the two there. You can also play with the altitude. Let me just also get this here. Say C5. And let's get a yellow color. But what will happen with the altitude? What will happen? What's your hypothesis? Let's make this 200 kilometers. What happens? I don't know why it's not letting me. It's weird. Okay. Let me change this. Maybe. Let me see if this works now. Oh, really? Shit. You're right. Oh, no, but it's not taking me here 900. No, I think this is the bug actually. You see that actually even very expensive tools can have bugs. It's not letting me put these 900 kilometers here. All right, let me check. Well, I think I managed. And let me just do one more. Just 200 kilometers more, so 478. So if you see here, I'm running. I have also 4 satellites with 200 kilometers altitude difference to each other. And if I move to the beginning of the simulation, let me just hide the others so that you can focus. So if you see, I mean, this is a constellation of satellites which have different altitude parameters. But now if I animate this out, this is the effect that we see. Even a very short period of the simulation, they will start to shift away, shift apart. Why this is happening? Because of the equation that we derived early morning, right? The velocity is dependent on the altitude. Yeah. The farther away you go, the slower you move. And even on 200 kilometers range, then they will start to separate each other in this way. So altitude sometimes is not the best parameter if you want to keep like a flight formation. Of course, they will eventually sync up again. I mean, they will separate and they will get together again, but this might happen in multiple days, if not weeks. So altitude is a tricky thing if you want to play with constellations. Let me just illuminate the others again. Something else, maybe I want to show you this. Let's leave just Leo B1 and this one over here. No, sorry, this one and this one. You're out. These one are overlapped. Okay, so I have only 2 Leos here. Let me just have again my view timeline. Sticky. Okay, I'm set. So I have my 2 satellites here. Now, something that will likely be interested in studying is the visibility condition between 2 satellites as well, because you want to also see which satellite can communicate with which satellite. And for doing this, you also can use the access tool, right? So you can click here, access, and you can select the source object. Let's choose B4, B3, B1 and B3, sorry, Leo B1. And we want to compute to the B3 here. I just click compute. And I get like sorry, I didn't express this AER report, AER, stands for azimuth, elevation, and range. These are the 3 letters. So, and here you can see that the contact that we have between the satellite is permanent. It's never ending, of course, because if we just animate now, let me zoom into Leo B1, right? And I just animate this out. Then these satellites are essentially, there is nothing blocking. Maybe the red color is not the optimal one. Let me just change this to white or something. So if you see here, there's nothing blocking this satellite from each other at any moment. And they're practically in line of sight all the time, right? So this is why if I go to the report says that the contact starts at the beginning of a scenario and the contact lasts until the end. But let's try to make this a bit more realistic. If we go to the report here, what we can see is that the range, sorry, this was the old one. This is the new one. Can go up to 2,300 kilometers, right? And 388. So this is the farthest away. Let me zoom time here, set animation time. And this is the moment where they are farthest away, right? Makes sense. Pretty much on the equator side, right? And this is where the satellites are the farthest away. Now let's say that I want LEO B1 here to have a range constraint. Let's say they have a transponder, an intersatellite link transponder that can maximum connect up to, I don't know, 2K or something. So we can go here to the basic constraint and say, I want a maximum range of, let's say, 1,800 kilometers. I just hit apply here. I will go to the report. I should refresh this out. And now you can see that I do have contact terminations here and a new contact that start afterwards, because now I don't have permanent visibility because I'm really meeting the range of my connection to this distance. And actually you can see that the contact terminates pretty much almost 1,800 kilometers. We can go to this time, set animation time. And if I very much animate this out, then the link is basically terminated there. I'm just going to animate this further. The link should be starting as they get closer to each other. Then we have link there. There is a link. It continues all the time because they're getting closer. But as soon as they fall apart, the constraints kick in and the link will stop, right? And you can start playing with this constraint quite a lot. So that you can start analyzing when satellites can see each other under which conditions and so on. Let me explain one more thing, and then I will just finish and leave you play on your own, which is you can get more specific here if you want, which is satellites will have antennas typically, and it won't be a matter of just computing the line of sight from in any direction, right? Like what you are doing now. We're doing is basically a sphere of range that you compute, right? And you want maybe to be a bit more specific. And one object in STK that is quite useful for this are sensors. So let's make here a quick experiment. I will delete the other satellites and leave these two. So here I will insert a new object. And if you go here, you can see ground station should be somewhere here, sensor. Yeah. Down beneath here, you have a sensor. You can define the properties here, and you can select to which object the sensor should be attached to. So let's attach a sensor to LEO B1. And let me just try to order the windows here. And by default, you see, I will close this. I will just leave the default just to visualize what happens. If I zoom to LEO B1, there is a default sensor that was attached to the satellite. By default, this is a conic sensor, right? And it's by default fixed in the satellite and it's aiming toward the surface part. And this can mimic like an antenna, this can mimic a camera, or this can mimic some coverage element that you want to analyze. And you can basically duplicate sensor if you want. I can just put another one. I would just put ISL for ISL, and this can be GSL for ground satellite link and ISL for intersatellite link. And then we right click on the ISL to say, well, I want this sensor to be typically intersatellite links antenna are typically narrow because you need to get very far away and you want to have very directive antennas. So let's say that I will have a 10 degrees antenna, 15 degrees. And I also want this antenna to be, if I only apply what I did, that will be a smaller antenna like the one here, right? It's an antenna with just a narrower cone. And now I want this antenna to point to the side. So you can go here to the pointing part of the sensor. And here I can say, well, I want this, the elevation of the sensor now is 90 degrees. If I hit 0, this should point to the forward direction, right? So I changed the elevation of the sensor. Now, if you see the sensor, is pointing towards the front of the satellite because I changed the elevation from 90 degrees to 0 degrees. And now I also want my sensor to be on the azimuth side to 90 degrees. Not, it should be minus 90 degrees. And now my sensor is, well, more or less pointing to my neighboring satellites, right? And now also I want to go to constraints here in my sensor and say I also want the maximum range of 1,800, as I mentioned before. So now if you see, we have created a conical sensor that is aiming to the left-hand side of the satellite all the time, right? And is fixed and attached to the spacecraft body, right? And this sensor is basically tied to the satellite. There is a moment where the satellite will cross on the poles, as we see here, and my neighbor will be on the right-hand side of my sensor. And if I am basically imitating an antenna here, I will be able to say, well, I can contact my neighbor at this point, and then at this point, not anymore because it's out of the cone here. And I can imitate this more sophisticated type of volumes computation. And to do this, I can go to Access. And here I can select my object and I can choose, instead of LEO B1, I can just choose the sensor. And I want to compute the access from my sensor to LEO B3. I can hit compute. I can go to the reported part if my laptop computes it. And now I have an access report, just like the one we have seen before, but now computing with the volume of the sensor that I have just configured, not just the line of sight, which is a perfect sphere, but my sensor. Maybe we can try to set animation time here. And this is the exact moment where the contact starts. Of course, very stupid because this is basically one of the satellite crosses each other. And let's go to the end of the contact. And this is the moment where they stop communicating. And you see that at this very moment, the satellite underneath is actually right getting out of the cone, right? So out of the cone, that you're out of the communication range. Any questions about this? And guys, I mean, in a nutshell, this is what I shared today. I think is already enough for you to play and try to, you know, make some exercises on your side. And pretty much you can model whatever you want, like ground stations. You can put places on the surface and compute how much time the satellite visits that place. You can play with the sensors. Maybe you can play with this sensor here as a camera, but that camera, you want to compute how many times that camera visits France, for instance, and you can put something there and make some analysis and export this data in this CSV file, these text-based files, and you can post-process those files in a Python notebook or whatever fits you. And this is basically kind of a quite powerful tool chain to analyze space and satellite systems. I'm open for any questions either now or either later on via email if you want. So I suggest, I mean, we can take a break and we can spend the next hour or so playing with the tool and we'll be available here for consultation. Great. Any questions? Good. I will stop the recording so that this basically also this recording is still available if you want to, because I know I talk too much and I move quite quick. But yes, you will have the recording in case you want to navigate over here. Yeah.